Let's compute the power. In an internal combustion engine, each cylinder runs through a power stroke once per revolution. If the engine is running at 2000 RPM, that results in 2000 RPM times 1 minute or 60 seconds to cancel the per minute. Remember, RPM is rotation per minute, so the minutes cancel, equals about 33 cycles per second. A car engine is a 4-stroke engine, which means that the power stroke takes approximately 1/4 of the cycle time. We have 1 cycle times 33 cycles per second is 0.03 seconds per cycle times 1/4, since a power stroke is 1/4 of our cycle time. So we see that our power stroke is about 0.0075 seconds. Using this time, we can compute the power, which is the rate of doing work. The power is equal to work divided by time. So that's our 0.597 kilojoules that we computed, divided by 0.0075 seconds, which is equal to 79.6 kilowatts. We can convert this to horsepower. 79.6 kilowatts times 0.7457 kilowatts per horsepower equals 106.7 horsepower. So that's about a 100 horsepower cylinder. If we had an 8-cylinder engine, we would have a pretty powerful engine, around 800 horsepower. Let's summarize. First, we wrote the work done by a change in volume as the integral of P dV. We recognized that in order to evaluate this integral, we needed a relationship between pressure and volume. A polytropic process relates the pressure and volume using PV to the n equals a constant. We then assumed that the power stroke was an isothermal or constant temperature process. An isothermal process has a polytropic constant of 1, resulting in PV equals C. We then solved the ideal gas law for pressure and substituted the result into the work integral. We integrated to find the work, resulting in work equals mass times the specific gas constant times temperature times the natural log of the volume ratio. We then used the ideal gas law to find the mass of air in the cylinder, as well as the temperature after combustion. First, we computed the mass of air in the cylinder at the bottom of the compression stroke. Then we computed the temperature of the unburned air-fuel mixture at the end of the compression stroke. We then added 500 Kelvin to simulate the combustion process. We evaluated the pressure at the end of the combustion process as an exercise in using the ideal gas equation of state. We then computed the work using our integrated result. Finally, we estimated the time that the power stroke takes, and from that computed the power of our cylinder. That concludes the example. Thanks for tuning in, and have a great day.